The parent function of the absolute value family, it's a v. When we do our table for our parent graph, it would start at -2 and go to +2. When you take the absolute value of a number, it's always going to turn that number or keep that number positive. Absolute value is a representation of a number's distance from 0. Distance is always going to be a positive value, so that's why we're talking about always having positive numbers. So none of my numbers will actually change, just the signs will change if they are negative. So now I'm going to plot these points. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And then we want to connect it so that it makes a V. We don't want to make it a curve like we did with the quadratic family. The domain is all real numbers because this graph would keep going left and right forever and ever. The range is going to be greater than or equal to 0 because the lowest point on my graph here is at what we call the vertex, which is at 0, 0. And since we're talking about that, we can go ahead and fill in this vertex. And that's always going to be at the corner of the graph. And then the end behavior, remember that for x's, you always need one of each. So one positive, one negative. And then your y values are always going to go in the same direction. So they're either both going to be going towards positive infinity or negative infinity. So positive infinity is our answer for this one because both arrows are pointing up. The first thing we want to identify is the vertex. So in our problem right here, it's at the point 0, 1. So I'm going to go ahead and fill that in. And now we want to find our a value. So I'm going to go right one box, and then I'm going to go up until I get to the graph. Since I went up 3 boxes, my a value is 3. So now I can fill out all of my transformations. I have a vertical stretch because of my a value, it's bigger than 1. And then this graph also shifted up 1. So my equation is going to be y equals, my a value goes first. I need absolute value of x. I don't have a horizontal shift, so that means x is the only thing in the absolute value bars. And then up 1 would be +1 on the outside. For domain and range, my domain for all absolute value family graphs is going to be all real numbers. My range will always be y, and then I'm going to use the number from my vertex. So I'm going to use this 1. Since this graph is facing up, it's going to be greater than or equal to 1. So off to the side here, I'm going to make a little note. If your graph faces up, range will always be y is greater than or equal to your k value. If your graph faces down, your range will be y is less than or equal to your k value. So since this graph faced up, that's why I used greater than or equal to. And then end behavior, I need one of each for x. Both arrows are pointing up in this problem, so that means both of my y values are going to go towards positive infinity. For problem number 2, my vertex is at the point -2, -1. My a value, if I go right 1 and down 1, that brings me to my graph, so my a value is -1. And what that tells me is that it's reflected, but it is not a stretch or a shrink. So for my transformations, I'm going to write that it was reflected. And then I also have to say that it's moved left 2 and down 1. So that would make my equation negative. Since it moved left 2 inside the absolute value, I would have x +2 and then down 1. The vertex, we figured out at the very beginning, is -2, -1. The domain is all real numbers, just like every single absolute value family graph. The range, since this one's upside down, I'm going to be using less than or equal to. And then I use the y value from my vertex, which is -1. For end behavior, both of the arrows are pointing down. So now both of my y values are going to be going towards negative infinity. The first thing I want to do is identify the vertex of this graph, and that's going to be centered in the middle of my table. So I'm looking at my h and k values. My h value is positive 1, because you always take the opposite, and then k would be negative 3. So now you're going to use your calculator, and you're going to plug this into y equals. And just so you know, in case you weren't in class or you forgot, in order to get the absolute value bars in the calculator, you press second and then 0, the number 0. It has the word catalog in blue written over it. And the very first choice is going to be ABS with a half of a parentheses. And that's what you want to choose. And when you type that in, it will bring up the absolute value bars into your calculator. So you're going to type this into your calculator, and you're going to go to the table, and then you're going to fill in 2 points above and 2 points below. So the 2 points above, when you're looking at the graph, would be -1, -5, and 0, -4. And then the 2 points below are 2, -4, and 3, -5. And one thing you'll notice, and this is going to be true of every single absolute value table that you should do, your numbers are going to match. So just like they did with quadratics, you're going to have your vertex in the middle, and then as you go out, you should have the same numbers. It should be symmetric. So now I'm going to plot these points. -1, -5, 0, -4, 1, -3, 2, -4, 3, -5. And again, it should be connected so that it makes a V. Domain is all real numbers. Range, since it's upside down, will be y less than or equal to, and then remember the y value of my vertex was -3. Vertex we already figured out, 1, -3. That was the very first thing we did. And then end behavior, both of my arrows are pointing down. So I need one of each x, and then both y's will be going towards -infinity. First thing we want to do is identify vertex. I don't have a k value, so I'm going to put +0 so we can see it. So that means my vertex is -1, 0. And now what I want to do is plug this into my calculator so that I can get all of my, my table values. So when I go to the table, I want 2 points above -1, so that would be -3, 4, -2, 2. And then the 2 points above would be 0, 2, and 1, 4. And again, you'll notice that the vertex is here in the middle, and then I have my symmetric numbers going out. So that's kind of a way you can check to make sure you're doing things right. Now I'm going to plot my points. And then I'll connect the dots so that it looks like a V. So my domain is all real numbers. The range is going to be y is greater than or equal to, because it's facing up, and then I'm taking the y value of my vertex, which is 0. X-intercept is talking about where this graph crosses the x-axis. So that's this point right here that I'm circling in green, and you want to write your answer as an ordered pair. So that would be the point -1, 0. That happens to also be the vertex. And then I want to find y-intercept. That's this point right here that I just circled in purple, and that is at the point 0, 2. And one thing I want to point out is that you can always see the x and y intercepts, if there are nice ones, on your table. Your x-intercept will always have a y value of 0, so that's this point right here. Oops, I used the wrong color. That should have been in green. So your x-intercept will always have a y value of 0, and your y-intercept will always have an x value of 0. All right, now end behavior is the last thing. Both of my arrows are pointing up, so both of my y values are going towards +infinity.